All right, let's talk some more about sequences and convergence. This is the definition of convergence that we talked about last time. It's very weird when you just kind of encounter it out of nowhere. It looks like a whole bunch of nonsense symbols. This is some real Hollywood-style mathematics. This is what it means to say the sequence AN converges to A, and we write this, lim AN equals A. Another notation, which I don't think I wrote this last time, sometimes in the book you will see just this, AN and then this arrow A. This means the sequence AN converges to A, all right? And what convergence means is all of this. It means for all epsilon greater than 0, there exists some n, a natural number, such that n is bigger than the big N, implies AN minus A is less than epsilon. And the sort of English language translation of this, in vague terms, this means when the n is really big, and then this over here means AN and A are really close together. All right? That's what that should be like your interpretation of this. So this means if the little n is big enough, then the term AN minus A in distance is very, very small, all right? But like I said, I've been saying, for a while, the true beauty of this definition is that you never actually say these words, n is really big, or, really what I'm saying here is I'm imagining that epsilon is really, really small. But you don't actually have to say that as part of the definition. That's the beauty of it. It's the hard definition, which is why it took so long for people to come up with this. But this is one of the cases in mathematics. Sometimes the definitions are more important than the theorems. Or like the big breakthrough in this case was not somebody proving a theorem that nobody else knew how to prove. It was just somebody making the definition that nobody knew how to make. All right. What I want to do today is just a bunch of examples showing that a certain sequence approaches a certain limit. So we did one very simple example last time. I'm going to do a few more complicated ones. I'm going to do one, and then I got some for you to try. So let's do... These are kind of complicated, kind of hard, but at the same time, they are still fairly formulaic. Like there's a certain pattern that you basically always do the same process, kind of. And so they are, I wouldn't say easy, but at least you don't have to think too much out of the box to do these. Unlike, some of the proofs on the homeworks can be a little tricky. Anyway, let's show that the lim of n plus 5 over n is, can anybody say? Now, one thing that you may have noticed is, in order to show that something approaches something, you kind of, like, if you're going to use this definition, you kind of already have to know what the limit is. So, a typical homework question might say, here's a sequence. First of all, tell me what you think the limit is, and then actually demonstrate that that really is the limit. So, any masters of calculus out there? What is the limit of this? 1. Yeah, it should be 1. How would you figure that out? With calculus. I suppose you could let the n become infinity here. You maybe use L'Hopital's rule if you want to get into that. Anyway, it's 1, right? Okay, let's try to show that this is 1. All right? You have to write a little proof here. Although, like I said last time, and like I said this time, the proof always has basically the same steps with an interesting kind of weirdness in the middle. So, as we did last time, I'm going to try to have the same format as last time. I don't know if you remember that, but it doesn't really matter. I'm going to begin by saying, let epsilon greater than 0 be given. And then we will show, actually it's more like, we'll find some big N, such that n greater than big N implies... And here I'm going to write in, instead of, I'm just copying the definition here, but instead of AN minus A, I'm going to actually use AN is n plus 5 over n. So I'm going to put that in there. Minus A, what is playing the role of A in this case? is 1. It is the limit. Yeah, this a is supposed to be the limit that it's actually converging to, so 1 right there. Less than epsilon, all right? This is what last time I labeled as step 1 of the proof. The turn in the magician's analogy. This is, the magician just shows you the ordinary object. Step 2, the magician makes that ordinary object do something extraordinary. This is when you actually say what the n is. Now, if you remember the proof from last time, I just whipped it out of nowhere and said, you just have to trust me, this is what the n is. And I said, this is what we're going to talk a lot about next time. How do you actually figure out what the n is? So for step 2 of the proof, maybe I'll label these steps just one more time. I'm not usually going to label them, but this is step 2 of the proof is let the big N, I'm going to say what it is. All right, but this is where there's a bunch of work that you got to do kind of on the side. It's not actually part of the proof, but you have to at this point figure out what the big N is supposed to be. So I'm going to actually do this all kind of in a little sidebar over here. When you read proofs like this that are, say, published in research articles, often all of this will be omitted, all of this kind of side work, and they just sort of pull the rabbit out of nowhere. They tell you what the N is out of nowhere. They're not just making that up. They did a whole bunch of work, which ends up not having to be actually part of the proof. But anyway, here's the idea. What you want to do is start with this thing here. And first of all, I'm going to simplify as much as I can. So it is absolute value. I'm writing all this in red because technically this is not necessary to include as part of the proof. But if you are doing the proof, you definitely need to work this out, or else you have no idea what the big N is supposed to be. So first of all, I'm going to say simplify as much as possible. What can we do to simplify that? The absolute value signs is a big obstacle, and there will always be absolute value signs in here. Can I do something about absolute value of the thing minus the other thing? Is that the same as absolute value of the first thing minus absolute value of the second thing? The answer is no, you can't do that. When you have things being added or subtracted, you cannot just split up the absolute values in the simplest way. If they're multiplied, you can do that, but not if they're added. So we can't do that. Anyone have another suggestion? Can we do anything to simplify that? Generally speaking, because I have these absolute values, I do not like to see things added together on the inside. I much rather would see things multiplied together on the inside. I don't know if that helps. Any suggestions? Multiply the n. I'm trying to simplify. You might say maybe multiply both sides by n, although there's not really another side to work with. Yeah? Yeah. What I don't like here is this subtraction. Let's just actually subtract it. So I'm going to make a common denominator in there and actually subtract the two things from one another. So this is equal to n plus 5 over n minus n over n. That's the common denominator, and that is n plus 5 minus n over n, right? And we can cancel the n's, right? N minus n go away, and we end up with absolute value of 5 over n. Can this simplify at all? I don't know, I like that. How, what else can we do? Yeah? Yeah, now we can actually ignore the absolute values, which is like that's always my favorite step when I get to banish the absolute values, because I don't like the absolute values. But it is true, the absolute value, 5 over n is definitely positive, because 5 is positive, and n is a natural number, so it's positive. So this is 5 over n. All right? So that thing, we simplified. That's what I said, simplify. That, right? Just did. Okay? Now, what we want is, we want that thing, which we just simplified to be this, to be less than epsilon. So over here, I'm going to say we need 5 over n to be less than epsilon, right? 5 over n is the same. It is equal to this, which we started with. So I wanted that thing, that complicated thing, to be less than epsilon. That's the same as 5 over n less than epsilon. And now we can, since I simplified, I can solve this for n. It will say 5 less than n times epsilon, and then I can divide by epsilon. 5 less than, I'll write it this way around, n greater than 5 over epsilon, right? And that is what I use for the big N over there. So this is all on the side. The true proof proceeds by saying let big N be greater than 5 over epsilon. The idea is, if this really is bigger than 5 over epsilon, that should be sufficient to ensure that all of that stuff is less than epsilon. Why is that going to work? Well, it's because I made it work. Like, that is why I chose this 5 over epsilon, in order so that all of this would actually work out. All right? But as you're writing the true proof, it seems like this comes out of nowhere. I mean, when you're doing this on your homework or something, I would expect you to also write this on the page. Like, how would we be able to tell where you got that? But this stuff over here in red, technically speaking, it's not really part of the main proof. All right? That was step 2 of the proof, figuring out what the n is supposed to be, and then saying what the n is. And then finally, the last step of the proof, which I call the prestige. This is the magician reproduces the object again as it originally was. We are going to actually demonstrate that this choice of the big N makes this inequality true. So for step 3, I will say then if n is greater than n, we have, and now I'm going to write a big string of inequalities beginning with, sorry, I'm going to have to scroll here. I'm going to start, you see on the very bottom there, I'm going to start with n plus 5 over n minus 1. I'm going to write a bunch of either equal signs or less than signs, less than, blah, 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 eventually ending up with epsilon, and then we'll be done, right? Because the whole point of what I'm trying to demonstrate is if n is greater than the big N, then this is actually less than epsilon. Okay, so if n is greater than the big N, hopefully I should be able to demonstrate that that really is less than epsilon. Can we do it? Here I'm going to either rewrite using equal signs or using less thans and end up with an epsilon at the very end, all right? How can we rewrite that using either equal signs or less thans? Well, using equal signs, I can do the same simplifications that I did in the sidebar, and this simplifies, it is equal to 5 over n, right? By the same stuff that I wrote over there. You can, I mean, if you want to, you can copy these details in here, or, I mean, I can see you already did that on the side, all right? Now what can we do? I want to maybe use less thans or something to end up with epsilon. How I end up writing this in terms of epsilons at all is I have 5 over n here, but the little n is bigger than the big N, and so I can do this, right? The little n is larger, so what I just did is I made the denominator smaller, which means this thing really is bigger than this thing. All right? Any suggestions about what we can do next? I'm going to keep on either simplify, use the equal sign, or do something using a less than sign. You can't simplify that. Yeah. Less than 5 over epsilon. The n, that's close, although not exactly what I want. Yeah? Yeah, 5 over epsilon. Because of this, the big N is bigger than 5 over epsilon. I replace the big N with 5 over epsilon. And now, just like a wonderful magic trick, all of this unravels, and that's epsilon, right? 5 over epsilon is epsilon. So if you want to just conclude, so this is less than epsilon, as desired. All right. That's how we do it. Yes?
So my
why do we replace big N with 5 over epsilon? The idea is to start with this and end up saying eventually less than epsilon. And I mean, at this point, what are you going to do to end up with epsilon? We have to somehow introduce epsilons into this formula. And so I mean, you can't do anything with 5 as just a number, but this big N somehow I want to turn into something involving epsilons, and we've already said up here this was the choice for the end. So that's really the only thing that you can do to make the epsilons work out. All right? Great. I got one for you all to try. You think we're ready for that? I think you're ready for that. I'm going to walk around and see how you're doing. It should, actually I have 2 for you all to try. But anyway, what you do should have exactly this same format. This is why I said these are kind of hard, but still there's a very specific structure to it. And basically, your step 1 will always say the same thing. You don't have to think at all. Step 2, you have to do this work. And then step 3, if you did step 2 correctly, step 3 should be more or less a routine thing where you just demonstrate that you actually end up with epsilon after plugging everything back into the formulas. All right, I got 2 for you to try. So let's try 2 plus 1 over root n converges to, anybody want to say, what should this converge to? Like I said, you have to just kind of guess what you think it converges to and then write the proof. If you guessed wrong, your proof will not work no matter what you do. Yeah. 2, yeah. When the n becomes infinite, that little fraction part becomes like 0. So yeah, this converges to 2. And then I said I got 2 for you to try. How about this one? N over 5 plus n converges to 1. That's not the same as the one we just did. It's upside down. The one we just did was 5 plus n over n. This is a little bit different. But it works out similarly. All right, this may take a few minutes. I want to make sure everybody's with it, though. Feel free to talk to your friends. I'm going to walk around a little and see how you're all doing.
You get it? Three is smaller than 5. Yeah. But 1/3 is good.
Oh, okay.
Big N is
So, okay, sorry. It's right, you're gonna,
Yes.
that's not right.
Master was 5.
And now we have, wait, where is it? Because I messed it up.
Because it was 5.
This is the one insert, when I took the one
Yeah.
where I did carry through. And so it's actually, yeah. But then you're here, that is. Sweet. And it's the big. Yeah. Oh, yes.
Because big N is small. So what happens here is you just made the denominator smaller. And that means the value fraction. Little confusing. I'm going to start writing my answer for the first one.
It does work out.
You have a folder in that one?
scrolled it away. Sorry, it's that. N over 5 plus n. Let's take another minute and then we can talk about.
Oh, we're just saying this is, but this is still less. No. Oh, it's not on the board. Oh, I didn't see it.
N over 5 converges to 1.
You can tell it's right. All right, let's talk about it. I know not everybody's finished, and that's fine. Everybody seems to be doing well though. So this is my answer for the first one. I think just about everyone finished the first one. I decided based on my work on the side here that my big N should be some number bigger than 1 over epsilon squared. And then everything just kind of works out. You can see lots of like little details in this. 1 over square root of 1 over epsilon squared, but all of that sort of unravels and you just get epsilon. That's the, I don't know about you, I find this somewhat satisfying when it actually works out. It's like a whole bunch of nonsense which ends up magically simplifying to epsilon. Why is it so magical? It's really because you chose this thing very specifically so that the magic would work, and then you just demonstrate, yes, the magic really works. All right. Anybody had questions about this one? I think as I was going around, pretty much everybody seemed to do this okay. One thing that nobody asked me, I don't know if anybody thought about this, but this step right here, which pretty much everybody said, 1 over root n being less than epsilon, and then solve for n, right? How do you solve for n there? You square on both sides, and then you rearrange. Did anybody think about that? Can you really square both sides of an inequality? Like everybody know, I mean, you can add the same thing on both sides. Yeah? Yeah, you should worry about if it's positive or negative. But even so, it's not like when I square both sides, that's different from multiply both sides by a number, right? Everybody knows if you multiply both sides of an inequality by a positive, you get it. Then you can do that. If you multiply both sides by a negative number, then it's fine, but you got to switch the direction. But here, squaring both sides is really, you're multiplying one side by a number and multiplying the other side by a different number, right? To square this, I multiply the right side by epsilon, and I multiply the left side by root 1 over root n. This is a little weird. I will tell you, The answer to my original question, are you allowed to just square both sides? The answer is yes, you are allowed. Although it is something to think about. It is allowed to do that, provided that they're positive. What if they're negative? Can you do that? Which I think it gets messed up if they're negative. Like for instance, -2 less than -1. If I square both sides, it now says 4 less than 1. So if they're negative, you need to change the direction. Maybe that's not such a surprise. Anyway, that's just a little something to think about. Everybody squared both sides and felt fine about it. It's all right. Check your privilege. All right. Okay, let's do the other one. And this one I saw some people finish, some people didn't. That's fine. N over n plus 5. This one also converges to 1. It's just the algebra you do when simplifying the fractions or whatever is slightly different from when we did this example before. But anyway, I'm going to say, here's my proof. Let epsilon greater than 0 be given. This is all just standard stuff. We'll find big N, a natural number, such that n greater than big N implies, all right, n over n plus 5 minus 1 in absolute value less than epsilon. Okay, so I'm going to do my little stuff in red here is my side work here. We need to simplify. This simplifying, again, will involve actually doing the subtraction by a common denominator. Now, depending on what you're looking at, you're going to have to use different tricks in this step. But since I have a fraction, the trick is you make a common denominator and actually combine the two terms. So this is going to say n over n plus 5 minus n plus 5 over n plus 5. That's my common denominator. And then you actually put it together, you get n minus n plus 5. Don't forget them parentheses up there over n plus 5, like so. And then the n's cancel, and I get a -5 up top. Right? Everybody with me so far? And then finally, I can do the absolute values, at least a little bit. The absolute value on top is just 5. So this is going to say 5 over, not a little bit, entirely. 5 over n plus 5, right? Take the absolute value of the -5 becomes 5. And absolute value on the bottom is just n plus 5 because n is positive. All right, and then I want to make this less than epsilon, so I want 5 over n plus 5 less than epsilon, and then I solve for the n, which involves moving stuff around. So multiply that, I get 5 less than epsilon times n plus 5. Solving for the n, you can distribute the epsilon and then solve for n, or you could divide by epsilon. Maybe I'll do it that way. If I just divide this through by epsilon and then subtract 5, it says that. 5 over epsilon minus 5. Or as I was walking around, some people solved it slightly differently. You got an equivalent thing to that. All right? This is what I'm going to choose for my big N. So I say let the big N be some number greater than this, 5 over epsilon minus 5. I always say greater than here rather than saying let N equal. This is slightly weird just because I keep on saying, how do we choose the N? Really, I didn't specifically choose the N. I just said choose N to be anything greater than this. You can't really put an equal sign there because this over here is not a natural number. It's a real number. This epsilon is probably not a natural number. So, but the N has to be a natural number. So that's why I always say let the N be greater than that. Anybody feel weird about this? Could this be negative over here? It's something minus 5. Isn't that possibly negative? Yeah, even so, if this really was negative, then I guess you could choose the big N to just be 1, right? Although, in general, this doesn't actually, it looks on the surface like this might be negative, but to me, it doesn't really feel negative because I'm imagining that the epsilon is a very small number. Like epsilon is something like 0.0001. That means 5 divided by epsilon is actually something like 5,000. And so this is going to be positive. This 5 divided by epsilon, since epsilon is super small, 5 over epsilon is a super big number. And then you subtract 5, no big deal. All right, anyway, let's just finish it off here. So I choose this for the N, and then hopefully say then let n, little n greater than big N, and we have, and hopefully everything will kind of unravel perfectly. It was n over n plus 5 minus 1. This simplifies directly, just doing the same steps, which I won't write again. Simplifies to 5 over n plus 5. Now I start plugging in the big N's. This is less than 5 over big N plus 5. And then n replaces with 5 over epsilon minus 5. So this says 5 over epsilon minus 5 plus 5. Somebody asked me when we write these out, do I have to write the step with the big N, or can I just jump all the way to the epsilons, from the little n to the epsilons? I said, you can jump all the way to the epsilons if you want to. I'm pretty much always going to write this extra step, although when you're doing these proofs, it basically always goes the same way, and this intermediate jump to the big N is always followed by plugging in the epsilon, so it's not a big deal to skip that if you want to. Anyway, this actually equals epsilon because I can add the 5's in the bottom. This says 5 over epsilon, and then those 5's cancel, and I just get epsilon. Right, that's how it's done. Any thoughts about that? I hope that you get some amount of satisfaction in seeing all of this work out to be epsilon at the end. You don't have to like it, I suppose, although there's something likable about that, in my opinion. Any questions about that? Great. I got a one which is a little bit more complicated, and then I had one for you to try which is a little bit more complicated, although we may not have time for that. So, those examples that we've done so far all involve the same basic structure, and really every example we ever do is basically going to be like these ones, although sometimes this business in the red zone here, sometimes you got to do some slightly fancier tricks in there. So I want to do an example which involves a fancier trick in that part. Let's show, how about this one? N squared over n cubed plus 2 approaches. First of all, what do you think the limit is going to be? You have to just remember some tricks from calculus or something. Yeah? Yeah, this is going to be 0. Why do you say that? Yeah, this is like, you can think of this as like a ratio of polynomials where the degree is bigger on the bottom, the exponent is bigger on the bottom, and so this is going to be 0. If the degree is bigger on top, then the limit does not exist, and if the degrees are equal, you get some kind of specific ratio of the coefficients. There are tricks like that from calculus. I hope you remember those tricks. They do not figure into the actual proof, but they help you to figure out what the limit is supposed to be. All right, let's do it. So I begin as always. Let epsilon greater than 0. We'll find the big N, a natural number, such that n greater than the big N implies this business. N squared over n cubed plus 2 minus the limit, which is 0, less than epsilon. I like that 0. It makes the simplifying a little bit easier. But you're going to see the simplifying will immediately present some problems. Anyway, I'm gonna start my little red zone here. We begin by simplifying, all right? So you can ignore the 0. This, of course, is equal to n squared over n cubed plus 2. This is my simplify step. And then, I think we can throw away the absolute values, because everything that you see there is positive. So get rid of the absolute value signs. N squared over n cubed plus 2. All right? And now we have a bit of a problem. So without using any kind of special tricks, I'm going to have to do a kind of trick that we didn't do in the other examples. The problem is, if I were to proceed exactly as we did before, I'm going to erase this after I write it because it's not going anywhere. But I would say something like, we need n squared over n cubed plus 2 to be less than epsilon, and then solve that for n. And this is a problem. Just because I have squares and cubes in there, you're not going to be able to solve for n. just because you can't. In this scenario, there's no good way to solve for n. So there's yet another trick. What we need is this to be true. Actually, maybe I will keep that written in there. The problem is you can't solve this for n. But here's a trick. It's enough if, check me out here. It's enough if n squared over n cubed is less than epsilon. What I did in that step was I ignored the 2. You have to think about what that does in the fraction. If I ignore the 2, what that does is it makes the denominator a little bit smaller, which means it makes the value of this fraction bigger. So if I want to show this is smaller than epsilon, actually it is good enough if I showed this is smaller than epsilon, because this fraction is a little bit bigger than that one. And I wanted this one to be less than epsilon, which means it's good enough if this one is less than epsilon, because this one is bigger than that one. Right? Why did I want to ignore the 2? Because now I can continue simplifying, and now it is easy to solve for the n. All right. So the moral of this story, and let me just say this, I can now simplify even more. I get 1 over n. Right? That's what the thing on the left side is. And then solving for n gives me n greater than 1 over epsilon. All right. This is the trick, this little it's enough if trick. You do this when the thing is too hard to solve for n. You simplify it, but it's not simplifying by just writing something else which is equal. You write actually something which is greater than that. Question?
So, another reason like why that works just being that like really small anyways,
Yeah, this is you should, when you look at this, you should think in a sense the 2 is irrelevant here. When n is a large number, that 2 really is insignificant. And that should give you the idea that probably it doesn't matter. I can probably ignore the 2 and the whole thing will work out just as well. Yeah. So this is a bit, I don't know, a bit confusing the way that I wrote it here. If I were doing this and everyone was familiar with how I write these things, I would do it this way. Start with what you start with originally, which is this. You simplify as much as you can, which in this case is not all that much. But then I say that is less than n squared over n cubed, which is 1 over n. All right? So the moral of the story here is when you're doing these simplify steps, not only do you simplify using equal signs, but if you want to, if you feel the need, you can also insert steps which use less than signs in your simplification. All right? You cannot put steps which use greater than signs because that messes up this it's enough that thing. But you can use less than signs if you want to. So this is how I would write this. I just start with that thing here. I simplify, usually just straight up simplifying, saying other things which are equal. But if you want to, you can use less than signs. And then I say, so n greater than 1 over epsilon, right? So the extra complexity here, if I were trying to say what this trick is, it's just, to say it simply, in the simplifying step, we can use, of course, equal signs, which is how we did all those other examples, or less than, all right? And I will say parenthetically, not greater than, all right? In the simplifying step, you can use equal signs or less thans. And you want to use less than sometimes usually you do this in order to throw pieces away of the formula that you don't like. And here I threw away the 2 because it makes everything much simpler, all right? This is the extra little trick. I don't think we have time for you guys to try one. Let's finish the proof though. So this, now the last part of the proof, well, I say so apparently my choice for n is greater than just 1 over epsilon is what we ended up with, all right? And then I'm going to do the prestige here. So I'll say then if little n bigger than big N, we have, and let's do it, n squared over n cubed plus 2 minus 0, of course. So again, I'm going to just copy the steps from the simplification, and you will see I can do this step here. Actually, I can go all the way to the 1 over n. It's just it has a less than rather than an equal. But that's okay, because in this part of the proof, I'm looking for less than epsilon anyway. So it's all going to work out just fine. So this, if I were writing a few intermediate steps, I would say n squared over n cubed plus 2. This is less than n squared over n cubed, which is 1 over n. And now I do my usual thing where I replace the little n with a big N. So this is now less than 1 over the big N. And then the big N I replace with 1 over epsilon. So this is 1 over epsilon, which is epsilon. All right. This is how we do it. So this is the moral of the story. In the simplifying step, with that big green, the pickle. In the simplifying step, you can use equal signs. You usually use equal signs, but you can also use less than. That's the point. All right, we'll start off with another example like this.